Time for video number 4. Video number 4. Let's look, now that we've looked at precipitation reactions, acid-base reactions, and we looked at electrolytes and predominant species in solution. Review that first video if you need to. Let's look at the 3 different ways we can represent reactions in solution on paper as equations, depending what you're after. There's the easiest one, there's the real one, and then there's the one that gives you the most pertinent information. Here we go. Molecular equations. That's what we've been doing this whole time. We haven't worried about whether something's strong or something's weak. It just makes it really easy to predict the products and to balance it, all right? So that's why we like molecular equations. Easy to do stoichiometry off of. So by far the most common one you're going to see in general chemistry is molecular equations. So all species are written as molecules, even though ionic compounds aren't molecules. We're going to treat them as molecules. Easiest to balance. Once we have that, then we can advance it and write everything as they truly exist in solution. What is the predominant form of that species in solution? Is it a strong electrolyte? Then it exists as ions. Is it a weak electrolyte? Then it exists as ions and molecules, but predominantly molecules, so we'll write it as molecules. Is it a non-electrolyte? Well, that exists as completely molecules. So that's a complete ionic equation. These are called ionic equations. So strong electrolytes are split into their cations and anions. So write all species in their predominant form in solution. So you need to be able to look at something in a molecular equation and go, that reactant is a strong electrolyte. Split it. That reactant is a weak electrolyte. Leave it as molecules. That product's a strong electrolyte. Split it into the ions. That product is a non-electrolyte. Leave it as molecules. You have to be able to look real quick and within a second or two go, that's a strong electrolyte, a weak electrolyte, or a non-electrolyte. And the only one that you change going from a molecular to complete ionic is a strong electrolyte because you split that into the cation and anion. And remember, strong electrolytes, soluble ionic compounds, strong acids, strong bases. Review that video over and over until it is part of your essence. It is in your being. All right. That's going to be, now, a lot of people like it because it's the most representative of reality. But it's the bulkiest. It's got a lot of stuff to it. It just goes on forever and ever. There's a lot of clutter. And you'll find when you do a complete ionic equation, there's ions that are the same on both sides. They didn't react. They're just floating around creating electrical neutrality in the solution. So a lot of chemists at the higher levels do net ionic equations. This is the favorite for veteran chemists. And we do molecular net and complete ionic in our head and just go straight to the net ionic equation, where all we want to include are the reacting species. The non-reacting species are called spectator ions, kind of like, you know, I went to see the Chiefs and the Chargers play once. One of my ex-students was the head cheerleader for the San Diego Chargers, even though I was rooting for the Chiefs. Sorry, Chargers fans. So that was fun to go. I didn't have a whole lot of impact in the game because I was in the stands. I was a spectator. No matter how much screaming I did, I had zero impact on what happened on the field of play, right? That's exactly what happens here. Spectator ions have zero impact on the reaction that's occurring, right? There'll be certain ions that combine in a precipitation reaction to form a solid. The other ions don't do diddly squat. So what we're going to do is take those spectator ions out. And you'll see they're exactly the same on both sides of the arrow, so they cancel out. And we only include those reacting species, those reacting ions. Right? And that just removes a lot of the clutter. And that's the one that we like the most. But again, molecular is most common. Let's do a mixture of precipitation reactions and acid-base reactions. Do the molecular equations just like we've been doing. And then we'll just add the complete and net ionic equations to it, just so you can see the story unfold. Let me throw one up there for you. Here you go. For the reaction between, looks like chromium-6 cyanide solution, never seen that before, with rubidium phosphate solution. Write the molecular equation, balanced molecular equation, always balanced, the complete ionic equation, and the net ionic equation for me. I recommend you pause this, do it, and see if you get what I got. I like to see how your brain goes from the molecular. Now remember, finish the molecular equation first and then do this. And then when you're done with that, do this. Don't try to go down and across at the same time. It doesn't work out. So don't try to figure out the complete ionic equation while you're still working on the molecular equation. You will get very, very confused. Remember, in the molecular equation, you're not worried if something's a strong or weak or non-electrolyte. Doesn't matter. You're writing everything as molecules. You only worry if it's strong or weak here in the actual ionic equations. So let's punch this out. You ready? Oh, fumble. I rolled a 1. Chromium 6 cyanide. Let's write that down. Never used that in my entire life. But that's the good thing about doing theoretical stuff. I can throw some really weird things at you. And that's with rubidium phosphate. Let's identify our ions. So cyanide's a -1. Chromium, therefore, is a +6 because there's 6 of the cyanides, right? Type 2 metal. Rubidium's an alkali metal, so that's a +1. And there's 3 of them, so phosphate, which you should have memorized, is a -3. I highly recommend you do that. Double displacement, right? Let's figure out what goes together. So the rubidium and the cyanide go together. And then the chromium and the phosphate go together. So let's look at our products here. Rubidium's a +1 cation. Cyanide's a -1 anion, anion. So they go together in a 1-to-1 ratio. So I'm going to get RbCN. And then let's figure out our other product. I don't know the state yet. I'll do that in step 3. Chromium's a +6. Phosphate's a -3. So the lowest common multiple between 6 and 3 is 6, not 18, 6. It takes 2 phosphates to cancel out 1 chromium. So I get 1 chromium and 2 phosphates. 1 chromium and 2 phosphates. Watch out for that. Now let's get our solubility rules. And again, if you're in a hurry on a test, do you see that the chromium and the phosphate's way higher charged than the rubidium cyanide? I would predict this to be my solid and the rubidium cyanide to not be. So this one we don't have, there's no cyanide on here anywhere. I don't see it. And remember, if you want, it says sodium and potassium, but in my class we're going to go all alkali metals with ammonium ion. So we're going to treat rubidium like we do potassium and sodium and say that's not going to form a precipitate without any exceptions. Phosphates, of course, very highly charged. They love to form solids. You know, exceptions of the alkali metals and ammonium ion. Chromium 6 would not be that exception. Where did I put my pen? So this I would predict to be my solid and that to be a solution. Again, it's possible to get 2 solids, but rare. Then we balance it last. All right, so I got 1 chromium, 1 chromium, 1 rubidium, 3 rubidiums. Okay. So if I put a 3 here, that would balance my rubidiums. That would give me 3 cyanides. Oh no, I have 6 cyanides. Crud monkeys! I have 2 phosphates and 1 phosphate. Double crud monkeys! So I'm going to need to do the phosphate. Doesn't matter, do the cyanide or the phosphate. Let's put a 2 here. That'll give me 2 phosphates. That then gives me 2 times 3 or 6 rubidiums. And now I have 6 cyanides. See that? So that took a little bit more work than we planned on. So 1 mole of chromium 6 cyanide plus 2 moles of rubidium phosphate will give me 6 moles of rubidium cyanide plus 1 mole of chromium 6 phosphate. Solid. And in lab, we could filter that out, weigh it out, do a bunch of cool stuff. Do like % yield if we wanted to. We could calculate the maximum theoretical yield, do it in lab, get the actual yield, divide them times 100, get the % yield. That'd be a cool lab to do. But that's not the purpose. Now, nothing new there. Let's now work down. We worked left to right. We're done. We've got the 4 steps done. Now let's take a look at each species in turn. This reactant, that product, and answer the question, is it a strong electrolyte, a weak electrolyte, or a non-electrolyte? How does it really exist in solution? Let's look at reactant number 1, chromium 6 cyanide. Do you see the AQ there? I don't need any solubility chart. It's AQ, which means it's a soluble ionic compound. That means it's a strong electrolyte. You see that? So this is strong. So I'm going to put a little S here. That's a strong electrolyte. That exists 100% as separated cations and anions. So 1 mole of that is going to give me 1 mole of chromium 6 cations and 6 moles of cyanide. Cyanide is Cn minus, not Cn sub 6 minus. You have 6 Cn minuses. So let's write that. So that's going to give me a chromium plus 6 Cn minus. That's how you write 1 mole of chromium 6 cyanide in a complete ionic equation. That's how it really exists. 6 moles. So there's 6 particles of cyanide moving around for every 1 particle of chromium, zipping around in that test tube. Let's look at rubidium phosphate now. We're done with this one. Maintain balance coming down. If I have 2 moles of rubidium phosphate, now, is that a strong, weak, or non-electrolyte? It's an ionic compound. It's soluble, so it is a strong electrolyte. If it was insoluble, there'd be an S there, like that one. So that's going to give me, so when 2 moles of rubidium phosphate dissociate in solution, I'm going to get the coefficient times the subscript. 2 times 3 is 6 rubidium. See that? And then 2, and I have 1 phosphate here, times 2 gives me 2 phosphates. Do you see how people don't like the complete ionic equation? I only did the reactants and I'm already across my whole stupid board. But that's how 2 moles of rubidium phosphate. Now remember, you can't change the identity of these ions. Rubidium is Rb plus, not R. See, I see a lot of students do this. Because they, or they do this. No, no, no. Rubidium is not a triatomic ion. It's not a polyatomic ion. This is rubidium. Do you see that? Don't change that. There happens to be 6 of them. I see that all the time, every semester, right? Going on 30 years now. It's insane. All right? Do not, so that's why I like you writing these. Do not alter the identity of cations and anions once you've identified them. So please write that down so you don't make these mistakes. All right, strong electrolyte split, strong electrolyte split. Now let's look at our products. If you can do it all the way across, do it. I ran out of room. So rubidium cyanide is an ionic compound. It's soluble, so it's a strong electrolyte. Let's write that down. So this one was strong. This one is strong. Oh, are you seeing a pattern? So what does 6 moles of rubidium cyanide look like in solution when it dissociates? Well, I'm going to get 6 rubidium ions and 6 cyanide ions moving separately for each other. So I'm going to get 6 rubidium ions and 6 cyanide ions. Right? Just working down. Do this one, do this one, do this one, and then let's do the last one. So let's look at product number 2, chromium 6-phosphate. That is an ionic compound that is insoluble. That is categorized as a non-electrolyte. So we're going to write that as a molecule. Even though it's not a molecule, we're going to write it as if it was. So that we don't split. Keep it exactly the same. That is your complete ionic equation. That is how they really exist. Can you see how this is nicer, easier to balance, easier to do stoichiometry? That one, nobody likes complete or total ionic equation. I've seen people call those total ionic equations as well. Who cares? Now, let's try to identify. To go to the net ionic equation, we want to get rid of the non-reacting species, which are the spectator ions. So let's take a look. I'm going to take my green pen, and let's underline things that are exactly the same on both sides. Do you see chromium 6 plus aqueous on the right side of the arrow? No, it's tied up in the solid, the chromium reactant. Chromium's a player. That's the football player on the football field. It's not sitting in the stands. How about 6 Cn minus? Now, it has to be the same identity, same charge, same state, same coefficient, same everything. 6 Cn minus on the left-hand side. Do you see the 6 Cn minus on the right-hand side? The cyanide ion did diddly jack squat. It was a spectator. I like to underline my spectator ions to remind myself what to remove when I go to the net ionic. So the complete ionic equation, you just copy, paste, and remove what's underlined. I see 6 rubidium plus 1 ions in the aqueous state on the left. I see 6 rubidium plus 1 ions on the right-hand side. So those are also. So the rubidium ions and the cyanide ions are my spectator ions. I see two phosphate ions on the left, but they're tied up in the solid, so the phosphate ions react. Let's rewrite this now. I'm going to keep the chromium-6. I'm not going to include the underlying cyanides or the underlying rubidiums, but I am going to include the two phosphate ions. That's everything on the left. Get rid of the rubidium, get rid of the cyanide, only the solid on the right-hand side, the chromium-6 phosphate. Oh, isn't that so much nice and clean? That's the net ionic equation. It only includes the ions that react to form the solid. And it really hones your eyes into what is the driving force, the formation of the solid. You'll see this true with acid-base reactions later, is that driving force of water. You can do that. Not too tough. Let's do one with a strong acid, and let's do one with a weak acid, because those are treated slightly different. Remember, strong acids are the hydronium ions and the anions. They split. Weak acids are weak electrolytes. They stay as molecules, so slightly different. Let's do a neutralization or acid-base reaction now. For the reaction between HSCN aqueous, we know it's an acid, may not be one you're familiar with. Thiocyanide, is that thiocyanic acid? Not sure off the top of my head. It's a weird one. SCN minus is a polyatomic ion you may not have run into. But it doesn't matter. It's an acid. And calcium hydroxide. And remember, we're treating those as strong bases. Take a look. Is that one of the 6 strong ones? If it is, treat it as a strong acid. If not, treat it as a weak acid. Pause it. Do the balanced molecular equation like we've done before. The complete ionic and net ionic equation. That one. Let's see if we get the same thing. Let's do this. Here we go. HSCN aqueous. I was nice enough to give you the formulas. Plus CaOH2 aqueous. What are we going to get here? Let's look at our ions. There's our cation and our anion. Over here we've got calcium, which is an alkaline earth metal with a +2. See the H plus and the OH minus? That's where your water comes from. So let's circle those. That's our water. And then we're going to get the salt, calcium, thiocyanate. Oh, I just made that one off the top of my head. I think it's thiocyanate. That's a -1. Doesn't matter what it is. That's a -1 charge. So there's 2 of them needed to balance the calcium. I don't think I have room for that. So let's put it down here. And we know the water's a liquid. This one would be tough to do on the solubility chart because we don't have anything, right? I don't see calcium on there anywhere. There's no calcium, and I don't see SCN minus. Now, do you see CN minus? No, it's not on there anywhere. So this is not going to help us. So we're going to have to think, all right? I don't see either one of those. Now, in lab, we would have noticed that we would have had 2 clear colorless solutions forming a clear colorless solution that got warm. So we would indicate in lab that we know we didn't see any particles. SCN minus is pretty big, and it has a -1 charge, so really small charge there. So it's highly unlikely it's going to form a solid. But this would be a tough one to do on a test because we need more information because it's not on the solubility chart. All right. So that's something where I may have actually told you in the problem on a test. You know, clear colorless solution plus clear color solution forms a clear color solution that feels warm to the touch. And you go, oh, okay, so there's no solid in that one. That was a tough one. Let's balance it. 1 calcium, 1 calcium. I got 2 of the SCN minus, so I need to put a 2 there, which means to get 4 hydrogens, I got to put a 2 there. Acid-base reactions are pretty easy to balance. Remember, I'm not worried about things being strong or weak yet. Weak and strong acids react the same way. We're treating that as a strong base. Now we got to worry about if it's strong or weak. Let's do the complete ionic equation. Look at this species, strong, weak, or non-electrolyte. This species, strong, weak, or non-electrolyte. that species, strong, weak, or non-electrolyte, that species, strong, weak, or non-electrolyte. You only split the strong ones. Weak electrolytes and non-electrolytes, you keep them exactly the same. You don't alter them, but the strong ones you split. That is a weak acid. Do you see the HSCN? That's not HCl, HBr, HI, HNO3, H2SO4, HClO4. Those are the 6 strong ones. So that is a weak acid. This is weak, 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 weak. That's a weak acid. So that stays exactly the same. Its dominant form is the molecule. Right, so we're not going to change that. Let me do that down below here. Let me erase this. In case you get confused, I'm going to put weak here. That's a weak acid, right? Now let's look at the calcium hydroxide. We're going to treat that as a soluble ionic compound. So we're going to split that, and that's going to give you, and we got 1 mole, so it's going to give us 1 calcium plus 2 hydroxides. See that? 1 times 1, 1 times 2. So if we look at this, that's a strong electrolyte, right? So we split that one. Now let's go over here. Do you see the liquid there? Water, that's a covalent molecule. That's a non-electrolyte. Anything that's a liquid, solid, or gas, we're treating as non-electrolytes. It's only aqueous phase strong species that we split. So this is going to be a non-electrolyte. It's the non of the family. So let's write our 2 waters. And then last but not least, let's look at this one. That is an ionic compound. That's soluble, so that is a strong electrolyte. So we're going to split that. So 1 mole of this gives us 1 mole of calcium and 2 moles of SCN minus. So let's split it. There's 1 calcium. Woo! Didn't leave myself a lot of room to write there. And the 2 thiocyanates. There's your complete ionic equation. Let's do the net ionic equation. Do you see anything that's exactly the same on both sides? Do you see HCN minus on that side? I don't. It was rendered asunder. You see a calcium? Ooh, I see 1 calcium on both sides. That is a spectator ion. It didn't change. Do you see hydroxides on this side? No, they got tied up in the water, right? So really what's happening is the OH minus is extracting an H plus to form water, freeing up the SCN minus anion. So let's copy and paste the complete ionic equation and just omit the spectator ion. So we're going to keep the weak acid, forget the calcium, just get the hydroxides from that strong base moving around. We get the 2 waters, drop the calcium. Wada bing, wada boom. That's your net ionic equation without the calcium ions. We got 1 more to go. Whoa, there goes a hawk. All right, let's do one with a strong acid, which is a little bit weird. Here we go, the culmination of it all. So we did 1 precipitation example, 1 weak acid example. Let's do 1 weak acid. Strong acid. Blah, 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 blah. I need some lunch and caffeine. Here we go. Although I just told you what was in here. Let's write our species down. Remember, I don't care if it's strong or weak in the molecular equation. Let's take our hydrobromic acid. I'm nice enough to give you formulas. Let's take our lithium hydroxide. Let's figure out what our products are. What are our ions here? All right, bromide we know is a -1, right? There's our H plus. So there's our acid. Lithium's a +1. That's an alkali metal. Hydroxide's a -1. There we go. I think that's the most important thing you can do. I'll reiterate that every single time. If you did that, you won't make all the silly mistakes I see students make constantly, every year for 30 years. We're going to get water. Are you seeing a pattern here? Let's write our water down. The H plus from the acid, the OH minus from the base. And that will be liquid, right? And then we're going to get the salt, water plus salt. Lithium is a +1. The bromide is a -1. Ugh. So any outie. We're going to get lithium, bromide in a 1-to-1 ratio. Always put the cation first, right? Cation always goes first. So we're going to get lithium bromide. Now that's a salt. Let's look at our solubility table. Now we didn't include it but I want you to cross out sodium and potassium. Just put alkali metals, which would be lithium. And there's some exceptions to that, but I'm going to generalize it in my class. And there's bromide, which doesn't form solids unless it's with silver, mercury 1, that's the polyatomic one, and lead. So that's not lithium. So it looks like the lithium bromide is going to be AQ. And again, we'd mix it in lab, clear color solution, forming a clear color solution. Feels warm. That driving force of water releases a lot of energy. It's an exothermic reaction. And since they're all +1, -1, that's already balanced. Woo! Nice. Let's do the complete ionic equation. Now remember, look at each species in turn. Is it strong or weak? That's a strong acid. So we're going to split that up, baby. All right, so let me erase this. So we can put whether, so you don't have to do this, but I want you to realize what's strong and what's weak. This is a strong acid. So what you need to do is look back, and when I talked about strong electrolytes, strong acids react with water. So HBr attacks water, donating the H plus to form H3O plus. The hydronium ion plus the bromide ion. It does not dissociate like a salt. It's not a salt. You don't get H plus. Now, some places, especially introductory chemistry, just split it like that, H plus. That's okay. It's an oversimplification, but it's not reality. Reality is it donates an H plus to water to produce hydronium ion. We're going to do that for our general chemistry class here. No H pluses in solution. This is a soluble ionic solid. It's a strong base. So we're going to split the lithium hydroxide. Everything we got one of makes life nice. So split the strong acid, split the strong base. Water is a non-electrolyte, right? Anything that's a liquid, gas, or solid, we don't split. So we're going to get the water. That's a soluble ionic compound. That is a strong electrolyte. So that we're going to split into, we got 1 mole, so we get lithium plus bromide. There you go. That was pretty good. Now, what's tricky about this is when you go from H plus to H3O plus, you unbalance it. That's the only problem with using H3O plus. It's more reflective of reality, but it messes it up. See, now we've got 2 oxygens on the left-hand side and only 1 over here. So the trick is, whenever you use hydronium, effectively you're going H plus plus water. We have to add, for every hydronium, an extra water to the other side. So whenever you use H3O plus, however many H3O pluses you have on this side, you have to add that many more waters to the other side. Right? So if you see people using H plus, you could switch this just by converting H plus to H3O plus and adding that many waters to the other side. Do you see any spectator ions? Hydronium on the left, not on the right, but I do see a bromide here and a bromide there, lithium there, lithium there. So the driving force is the hydronium and the hydroxide forming 2 waters. So let's rewrite this without the lithium and the bromide spectator ions. So let's put the 1 mole of hydronium plus 1 mole of hydroxide, giving us 2 moles of water. And in introductory chemistry, you probably did H plus plus OH minus, giving you 1 mole of water. There you go. I can't give you any anything else. I could give you thousands of reactions from just these three, but they're all the same. You got this. Let's do redox next.